Welcome everyone to our video for resolving class imbalance problem for LiDAR-based object detector by balanced gradient and contextual ground truth sampling. I am Daeun, majoring in statistics at Korea University, and the corresponding author is Professor Jinkyu Kim. Most of driving LiDAR point datasets suffer from the problem of the class imbalance. As you can see below, for instance, car is the most major class, whereas cyclist or motorcycle class is one of the minor classes. However, in the real world, AV should detect not only major classes but also even minor classes. It is a very important problem. Therefore, in this paper, we present a way to solve this class imbalance. The method we propose consists of two. The first one is gradient balanced per class detection heads. First, we divide the detection head by class to prevent minor class dominance. And in the process of balancing each detection head, we use multitask learning techniques. This is because multitask learning can help to obtain a more accurate learner for multiple tasks. Furthermore, our total loss per detection head is like below. It contains location, classification, and direction loss. And finally, to balance each detection head, we introduce gradient balance techniques like below. We use a temperature T to control the strength of gradient balancing, and through this, we can give weight for each head in consideration of the loss change rate of each task. The second one is contextual aware LiDAR point augmentation. Data augmentation has been widely applied to object detection. In this kind of situation, our model uses prior semantic information to sample ground truth point in the realistic position. The process of method is way simple. First, we make ground truth database in the whole trained dataset, and after that, we determine where to introduce sampled object in the scene via semantic information. Therefore, this is a comparison of the mentioned process. A has input image and semantic information, and the previous point cloud sampling methods shown in B and C. As you see, they are not all reasonable samples because they sampled by random. In this situation, we proceed with regional point augmentation using semantic information as shown as D. The next part is experiment result part. We conducted experiment on KITTI and nuScenes, and both datasets shows that our method is more effective than previous method. Especially, our model exceeds the performance of baseline for minor classes in KITTI dataset. Also, we conducted obligation study to prove effect of contextual sampling. Not only point plus, our method shows performance improvement in other two models. Therefore, it can be sufficiently used as a plug-in method. We also conducted experiment on nuScenes validation dataset. Our model shows large performance improvement, especially in minor classes. Also, the following is figure comparing our prediction with previous method. Due to the influence of contextual ground truth sampling, our model shows a much lower false positive than before. For more information, please refer to our paper. Thank you for your attention.